Alright, so in this video I'm gonna be explaining a comparison of strategies for source-free domain adaptation. So this article in 2022. Data sharing restrictions are common in NLP, especially in the clinical domain. But there is limited research on adapting models to new domains without access to original training data. Because of the privacy issue. So a setting known as source-free domain adaptation, we will talk about this source-free. So we take algorithms that traditionally assume access to the source domain training data, active learning, self-training, and data augmentation, and adapt them for source-free domain adaptation. Then we systematically compare these different strategies across multiple tasks and domains. We find that active learning yields consistent gains across all SIM. I will create a playlist for active learning because it's very important for systematic annotations of unlabeled data. We put human in the loop, so our model suggests which annotation, which sample should be annotated, which unlabeled data should be annotated, and the expert does that systematically because the machine has suggested that label. So maybe it is because it's near the border in the classification, or the probability is small, the uncertainty is too high, so we don't know exactly about it. But I will explain this active learning in a different playlist. Recently, there is a rising interest in computer vision to develop methods for unsupervised source-free domain adaptation. Several works utilize a generative framework with a classifier trained on source data to generate labeled training examples or transfer the target examples to match the source style. Other works use self-supervised pseudo-labeling. For example, Leong in 2020 proposes source hypothesis transfer that freezes the classifier of the source model domain but fine-tunes the encoding of the source model with a goal to reduce the entropy of individual output prediction while maintaining a global diversity. They also augment the strategy by self-supervised pseudo-labels via the nearest centroid classifier. Select low self-entropy instances as class prototypes and pseudo-label the remaining target instances based on the distance to the class prototype, and progressively update the model on target data. The previous video was something like this. This idea is very close to the previous video. Self-training trains a model on a labeled dataset and then iteratively makes predictions on an unlabeled dataset and retrains. On each iteration, the examples in U that the model labels with high confidence are added to L, and the model is trained on the new larger L. This process is repeated until no more predictions are highly confident. Self-training has been applied to a variety of domain adaptation scenarios, but always with the assumption that original labeled data is available at each iteration. In source-free domain adaptation, L is not available, so source-free self-training could train on only the pseudo-labels, and it is unclear whether that would yield a superior or inferior model. So active learning selects a small number of examples to be manually annotated using strategies designed to select the examples that should most benefit the model. So the model suggests that. Various active learning, of course, there is a branch of active learning, we call it competitive learning, that also adds the label data that the data as a label. Those data we consider put them in the labeled package if they are very, very confident. Active learning is also frequently used in domain adaptation. For example, Chan in 2007, they applied uncertainty sampling for domain adaptation and word sense disambiguation models. And Ray combined model confidence and a domain discriminator to select target domain examples for sentiment analysis. So active learning typically assumes that the source domain data is available and can be combined with target domain examples. Thus, the efficacy of the source-free active learning is currently unclear. Data augmentation. Of course, we have used data augmentation in contrastive learning. If you watch my playlist for contrastive learning, especially in the unsupervised setting, it is essential. In computer vision, it's very easy to rotate and create data augmentation, but in NLP, it's still in its infancy. So data augmentation enhances limited data by using existing resources. A variety of data augmentation techniques have been proposed. And so we select these tasks because they represent real-world data sharing problems. The annotation schemes are complex enough that the model cannot be easily solved by manually annotating the target domain. And these two tasks suffer a large performance loss under domain shift. The source train model is 15 plus points of F1 lower on a target test set than on the source test set. And the popular Amazon review sentiment analysis dataset violates the points above. Label source and target data are easily available. The annotation scheme is easy. It is artificially balanced and removes reviews with natural labels, as others have noted. And the source domain model performs well in the target domain. We nonetheless include some experiments in this dataset in Appendix A. We find that with simple data pre-processing and source domain hyperparameter tuning, the source domain model alone outperforms all domain adaptation models. So these are 6 research questions. How much can we gain from having human intervention and not just the model alone? For active learning, given a fixed annotation budget, is it better to do several iterations of selecting examples of annotation and retraining the model, or to select and retrain just once? Because you can, for example, the model suggests something and the experts do annotate based on the model suggestion. But how many times this loop continues? This is the research question number 2. Of course, we should map the research questions to research objectives. How are we going to do that in a novel way? So the third research question is, for self-training, given a fixed confidence threshold, is it better to do several, as I said? So in each iteration of active learning or self-training, should we use the training data from previous iteration or start anew? And in 5, in each iteration of active learning or self-training should we continue training the model from previous iteration or the model from the source domain? Do active learning and self-training improve with data augmentation or work better alone? We design source-free variants of self-training, active learning, and data augmentation that incorporate the following parameters, allowing us to investigate the questions above: the maximum number of iterations for self-training or active learning, the data consistent construction strategy, which is S sub D, keep data to keep the training data from previous iteration, or reset data to start anew on each iteration. And S sub M is the model training strategy. Keep model to continue training the model from the previous iteration or reset model. And S sub A is whether or not to use data augmentation. Algorithm 1 presents our self-training algorithm, and however there is no source domain labeled data, so the model can fine-tune only on the pseudo labels. The remainder of the code ensures that models or data are kept, reset, or augmented as per the selected strategies. Self-training requires a measure of model confidence on each prediction. In both tasks, we add pseudo-labeled training data a sentence at a time, so we measure confidence at the sentence level. In negation detection, we use the predicted probability at Roberta's special sentence initial token. So this is the algorithm. We are given some source domain model, the unlabeled target data, self-training threshold, maximum number of iterations, data construction strategy, the model training strategy, the data augmentation, is it true or false? Then we copy this source domain model and the unlabeled target domain data. Then we go through this loop. We keep the data. So depending on data augmentation or reset model or keep data, we update the unlabeled target domain data. But in the second algorithm, it's source-free active learning. We fine-tune M on L. This algorithm presents our active learning algorithm. It follows an approach similar to 2021. Like most active learning algorithms, the core is to select examples the model is uncertain of. So here we find those samples that are very uncertain. For example, 1 minus probability is low or a high, because if P is 0, so this should be high. And then, like most active learning, the core is to select examples of uncertain. So since our development set are already annotated, we simulate the annotation by simply revealing the labels of the selected examples. Active learning requires a measure of model uncertainty on each prediction. In both tasks, we add annotations a sentence at a time, so we measure uncertainty at the sentence level. In negation detection, we use the predicted entropy at Roberta's special sentence initial token. In time expression recognition, we use the average of the predicted entropies of the tokens in the sentence. So we can also use a pool-based data augmentation to automatically increase the size of training set.